Good morning. Myself Dr. Lipika Das Samanta, Assistant Professor, Department of Chemical Engineering, Haldia Institute of Technology. Today I will discuss the Reynolds Transport Theorem. Before I will discuss the Reynolds Transport Theorem, first I will discuss the concept of control volume and control system. In the conservation equation, this equation is analyzed in two ways. First one is control volume and second one is control system. So what is control volume? The region of the space for analysis is called the control volume. Control volume is a geometric characteristics. The space is covered by the bucket. Bucket can be considered as a control volume. And the control system is the collection of the mass particles which is defined as a control system. For example, suppose there is a bucket is filled full of water, so which is considered as a control system. The handful sand is collection of the sand particles and also considered as a control system. If psi is the property of the fluid, the change of size can be written as d psi by dt at control mass approach and d psi by dt at v in the control volume approach. The surface which bounds the control volume Cv is called the control surface Cs. Next, different types of control volume. There are three types of control volume. First one fixed control volume, second one is moving control volume, and third one is the deforming control volume. The first, what is fixed control volume? A specific region in space that remains stationary or unchanged over a time and which is used in fluid mechanics and thermodynamics to analyze the system where mass and energy can flow across its boundaries. It is a conceptual tool for applying conservation laws like mass and momentum to the open system, where the focus is on the region than the specific mass of fluid. Second one is the moving control system. Define a region in space that moves with a constant velocity relative to a fixed reference plane, often used in fluid mechanics to analyze problems involving fluid flow where the control volume itself in a motions. Third one is the deforming control volume. Defined region in space, those volume or space changes over a time, unlike static control volumes that remains fixed or moving control volumes that maintain their shape while translating. These deforming volumes are essential for analyzing fluid flow problems involving complex geometrics, moving boundaries, or situation where the volume itself is expanding or contracting. The shape of the volume, control volume is changing. Next, I will discuss the Reynolds transport theorem. So first we will discuss what is Reynolds transport theorem. The Reynolds transport theorem says that the rate of change of an extensive property of a system with respect to time is equal to the sum of the rate of change of property per unit volume for a control volume and rate of efflux of the property. That means the theorem is the major theorem that helps to derivation conservation laws like conservation of mass, conservation of momentum and conservation of linear momentum, etc. So what is the equation of Reynolds transport theorem? The following general form of the Reynolds transport theorem is dB by dt system equals to del by del t triple integration and control volume B into rho into d drag plus double integration control surface D into rho into V bar into n cap into dA, where B is the capital B is the extensive property, small b is the specific property, which is equals to capital B by m. Here small m is the mass, rho is the density, n cap is the unit direction vector, drag is the volume, and capital V is the velocity. After that, I derived the Reynolds transfer theorem. In the figure shows the boundaries of the system and the control volume. The control volume is the portion used for the analysis, and this figure has a fixed control volume, and the system is set of mass small m or bunch of molecules. In this case, the volume of control volume remains constant here. For example, for a water held in the bucket is considered as a control volume, whereas the water is considered as a system. So, we consider the all extensive properties denoted by capital B, and here the intensive properties can be denoted by symbol small b. So in this case, small b equals to capital B by small m. Therefore, at the time t, the relation between properties of the system and the control volume is given by capital B system at time t equals to capital B and control volume at the time t, means extensive property as the system at time t equals to extensive property in control volume at time t. After some time interval at t plus delta t, the properties of the system is given by capital B, means extensive properties at system at time t plus delta t equals to extensive properties in control volume at time t plus delta t equal plus extensive property out at time t plus delta t minus extensive property in at t plus delta t. This is the equation B. So the rate of change of property of system after the time interval of del t is given by delta B system divided by delta t equals to B system at t plus delta t minus B system at t divided by delta t. Next, put the values from the equation 1 and 2. Here we give the two equations. Delta B system by delta t equals to B at control volume at t plus delta t plus B out at t plus delta t minus B in at t plus delta t minus B control volume at t, and also rewrite the equations. Delta B system by delta t equals to B at control volume at t plus delta t minus B control volume at time t divided by delta t plus B out at time t plus delta t minus B in at t plus delta t divided by delta t. After that, taking limit both sides with delta t tends to 0, limit delta B system divided by delta t equals to limit delta t tends to 0, B control volume at t plus delta t minus B at control volume at t divided by delta t plus limit delta t tends to 0, B out at t plus delta t divided by delta t minus limit delta t tends to 0, B in at t plus delta t divided by del t. After that, There are 4 assumptions we require. First, limit delta t tends to 0, delta b system by delta t equals to dB by dt at the system. And second one, limit delta t tends to 0, delta b at control volume by delta t equals to delta b by delta t at control volume. And third one, limit delta t tends to 0, b out at t plus delta t divided by delta t equals to limit delta t tends to 0, b out m out divided by delta t, as small b equals to capital B by m. So put the value of capital V in this equation and put the finally got the limit delta t tends to 0, b out m out divided by delta t. After that, for the equation rho equals to m into drag, the further value of m is put in this equation and got the value limit delta t tends to 0, b out, rho out and drag out divided by delta t. And next, where the drag equals to a into x, where capital A is the area and x equals to distance, and put the value drag in this equation and finally got limit delta t tends to 0, b out, rho out, capital A out into x out divided by delta t. And finally we got as the value O out, V out equals to x by delta t, and put the value in this equation. So limit delta t tends to 0 equal into B out, rho out, A out, V out into delta t divided by delta t. So delta t will be cancelled out, and finally we got limit delta t tends to 0, B out, rho out, capital A out into capital V out equals to B out, rho out, capital A out into V out. And fourth one is the limit delta t tends to 0. Similarly, B in at t plus delta t divided by delta t equals to B in, rho in, A in and V in. Next, put the value of B for equation. Putting the value in equation 3, dB by dt at system equals to delta B by delta t at control volume plus B out, rho out, A out into V out minus B in, rho in, A in into V in. And also we can write dB by dt at system equals to delta B by delta t at control volume plus capital B0 minus capital Bi, where B0 minus Bi is the reflux and B0 equals to B out, rho out, A out into V out divided by Bi equals to B in, rho in, A in into V in. Next, describe the Reynolds transport theorem for mass. For mass, as the property, put capital B means extensive property equals to mass. So, small b equals to, put the value of capital V here, and finally small b equals to 1. And now putting the value in Reynolds transport theorem and finally got the value by the statement of conservation of mass, dm equals by dt equals to 0. And finally got the equation of Reynolds transport theorem for mass is equal to del by delta t, triple integral at control volume rho into b into d into drag plus double integration at control surface b into rho into v bar into n cap into dA equals to 0. Next, Reynolds transport theorem for momentum. For the linear momentum, b equals to m into capital V bar. So the small b equals to, put the value of capital B here, and finally we got the value of small b equals to capital V bar. Now putting these values in Reynolds transport theorem and finally got the d by dt small into V bar at system equals to del by del t at triple integration in control volume rho into V bar into d dash plus double integration and control surface rho into V bar into n cap into dA as per Newton's second law, d of dt into m into v bar equals to m into a equals to capital M, means force. So therefore the equation comes del by delta t triple integral cv rho into v bar into d drag plus double integration cs rho into v bar into n cap into dA equals to capital F. Third one equals to Reynolds transport theorem for angular momentum. So for the angular momentum, capital B equals to small m into r bar into v bar. So small b equals to, put the value of b, capital V here, and finally got r bar into v bar, and put these values in the Reynolds transport theorem and got the value equation d by dt into m into r bar into v bar equals to del by delta p into triple integration at control volume rho into r bar into v bar into d drag plus double integration control surface at control surface rho into r bar into v bar into n cap into dA, where d by dt into m into r into v bar equals to t, which is called the torque. Therefore the equation comes del by delta t triple integration and control volume rho into r bar into v bar into d drag plus double integration into control surface rho into r bar into v bar into n cap into dA equals to torque. Next, most important thing in Reynolds transport theorem, what is the Reynolds number? The Reynolds number is a dimensionless quantity which in use fluid mechanics to measure the ratio of inertial by viscous force aids in the prediction of the fluid flow patterns in various scenarios. While the turbulent flow is more common at high Reynolds number and laminar flow is more common is the low Reynolds number. So what is the laminar flow? Laminar flow is also called the streamline flow and type of fluid, gas and liquid flow which is fluid travels smoothly or in regular paths. But in turbulent flow is a type of flow of fluid in which the fluid travels in the irregular phase. So today I complete. And next we describe the using Reynolds number determine the flow pattern. Using numerical analysis to classify between the laminar and turbulent flow are very tricky. However, it holds greater importance in industrial as well as academic sections. So Reynolds number is an important dimensionless parameter that it defines the behavior of the fluid based attributes like viscosity or velocity of the field. So according to the values of the Reynolds number equals to Q into V into D by mu. So if the Reynolds number is up to 2300, the flow is said to be laminar because of the decreased flow rate, viscous force is more noticeable. And if the flow's Reynolds number is more than 3500, it is considered as turbulent. The system inertial force can be maximized by the faster and moving in uneven flow path. And transitional flow is defined as a flow with Reynolds number between 2300 and 3500. So today I complete here. Thank you.